Hello everyone. Today our discussion topics on chapter 3 is the microprocessor architecture and the microcomputer systems. First of all, the microcomputer initial operations and the 8085 bus organization. The MPU performs the primary four operations. First one is the memory read, then the memory write, then the IO read and the IO write. In this section, the memory read is for the read the data or the instruction. Write memory is the read or write the instruction or data on the memory section. And IO read the accept the data as an input, and IO write is for sending the data as the output devices. By the following steps, the MPU works. First one is to identify the peripherals or the memory locations with the addresses. Then transfer the binary informations by data or instructions. Then provide timing or synchronization signals for sequential input and output or data transfers. 8085 system bus. Here we have three types of bus: address bus, data bus and control bus. In this address bus section, we generally transfer the addresses. It seems that the address bus is the group of 16 line or general identifiers which are from A0 to A15. The address bus is unidirectional, that means the one directional one, and the bit flows from one direction from the MPU to the peripheral devices. By here, the 16-bit address lines are capable of addressing total 2 to the power 16, that means 65536 or 64 kilobyte of memory locations. In hexadecimal, that can be started from 0000 to the FFFF. Now, the data bus. The data bus is a group of 8 lines which are used for data flow, and they are bidirectional. There, the data range can be started from 00 to FF, which can denote it as 2 to the power 8, that means 256 numbers can generated by the data bus. Here is the diagram of MPU 8085. Here we can easily see that here is the address bus, which is unidirectional one, which starts from A0 to A15, and in the data bus section we have D0 to D7, which have 8 lines, and which one is the bidirectional one. It have arrow on this side also and this side also. That's why data bus is bidirectional. And again, control bus is also an one directional. Here the microprocessor is connected with the memory input and output. In control bus, it controls and operates, and the control bus, it generates the various signals and carry the signal with the signal lines to synchronize the signals. By these signals, the microprocessor is controlled. That's the reason it is known as the control bus. It always carries the control signals. There are not a group of lines like data bus or address bus, but the individual line that provides a pulse to indicate the MPU of operation on control signals. Then the memory read operations. By this diagram, we will know how the memory read operation will work. First of all, the address line or the address on the bus is decoded by an external logical circuit, and the memory location is defined. Then the MPU send a pulse which is called as a memory read to the control signal. That means first of all we need to know the address and then decode by an logical circuit. In this section of MPU, first of all, a signal will generated, which one is the MEMR, and then it will go to the memory decoder, and then the address will be generated, and this address will send a MPU sends a pulse which is known as the memory read and control signal. Then the pulse will achieve and active the memory chip. Then the content of memory location, which is 8-bit data, are placed on the data bus and brought inside the microprocessor. That means that first of all the MPU generates a signal which is known as the MERE, which is the read signal, hit the memory chip section. Then the address bus will send an address of this in memory chip. In here we have the instructions and data, and finally by the data bus the data will transfer to the MPU section. That is how the microprocessor reads a data. Now moving to the next, this function is very important for your examination point of view, which is the internal data operation of 8085 registers. Here first of all we have the store section, then the arithmetical and logical section, then the test section, the sequence section, and then again the storing of data. We will describe it with an example. Here you can see that the functions of those registers are described in the reference of 5 operations, and when the processor executes the following 3 instructions, then the hexadecimal code of instruction are stored into the memory location, which is generated from 2000 to 2005 hexadecimal. This diagram is very much important for your examination point of view. Here your memory location is 2000, which is starts from 2000, and by 5 steps it will go to the 2005. Here the hexadecimal codes are occupied, and this is the mnemonic codes for those instructions. This one is the programming diagram that we have studied late in earlier sections. Here we have the stack pointer and program counters, which are very much important in this section. First of all, the program counter is a 16-bit register that performs the 4th operation in the list. What was that? The 4th operation in the list was the sequence section. So first of all the sequence section will occur in this function. Then the sequencing, the execution of the instruction. When the processor begins execute, then it places the address 2000 on the address bus and then increments it. First it places the 2000 on the address bus, then generally increases it. In the PC, that means program counter, to 2001 for the next operation, it brings the code 06, which is the 06 is the hexadecimal code to move the 2000 section to 2001. Then it interrupts the code and places the address 2001 on the address bus and then gets the byte of 78, that means 78 hexadecimal, which increments the address from PC to the 2002, and the processor repeats the same process with the next instructions. That does mean that first one is the sequencing one, and which is occupied by the programming counter section. In the program counter section, 2000 is incremented to 2001 by this hexadecimal code, and 2001 is incremented to 2002 by this 78 hexadecimal code, and that's going on, which is done by the program counter and the sequential section of which is the 4th number of execution section. Then when the processor execute the first two instruction, it uses register B to store 78 and A to store F2 hexadecimal binary, which is the operation number 1. What was the operation number 1? The operation number 1 is the storing section. That means the second instruction after sequencing will be the storing section. And now the third one. When the processor executes the instruction which is add B in the ALU, which is the operation 2, and it adds 78 to the F2 hexadecimal and results as in the 16 AH, which can generated by 78 hexadecimal plus F2 hexadecimal, which is the 16A hexadecimal. It replaces the F2 hexadecimal by 6AH hexadecimal in A, and it sets the carry flag, because here we can see that we have 1, 2 and 3. Here we have 3 sections 16A, but we have registers only for 16 bits. That is the reason 1 is on the carry flag section. So what was the number 2 number operation? Number 2 number operation was the arithmetical and logical. So first we have the sequence of the section, then we have store some data, then we have the arithmetical and logical operation. Now we are on the fourth section. In number 4, in this example, the additional operation generates a carry because the sum is larger. Which one is the 1? 1 is the carry section, and now it is larger than the size of the accumulator of 8 bit. To indicate the carry, the processor set a flip-flop which is called the carry flag to the 1 section and places the logic 1 to the flag register and to the position section. So by this we can understand, and now we are in the fifth section. The fifth operation deals with the components of the stack. The stack pointer is a 16-bit register which is used in the memory pointer. To identify the stack pointer, the read-write identifier is used to process the temporary storage for the data execution. So by that we can easily say that first of all we have the sequential operation, then we store the data, then the arithmetical instruction, and then we test the conditions. After testing the conditions we store the data again. So sequencing is the number 1 operation, then operation is storing, then arithmetical and logical operation, then testing the result, and then after all finally storing the data. This one is the internal data operation of 8085, which is very important for your examination point of view. Please practice this example at home. Now the peripherals or externally initiated operation. First one is the reset. Reset is to reset all internal operation and suspend all program counters and clear and holds the 000 address line. Interrupt is to interrupt an running work. Suppose you are running program A and then you interrupt program A and move it to program B. So that is the interruption section. Now the ready. If the signal is at the ready and point low, then the microprocessor enter into wait state. It will be waited to do some work. So ready is to get set and ready, but it is not going or moving. Now the hold section. In the hold section, the buses allows the external peripherals to use them. For example, the direct memory access. If the CPU wants to access the memory directly, then the hold function will be occurred. Then when the hold function occurs when the peripheral devices are holded and the direct memory access is granted for the CPU. Now the memory mapping section. We have memory addresses. Memory addresses provides the location of various memory devices in the system, and interfacing logic defines that the range of memory addresses for the each devices. In this section, we will discuss about a mathematical notation. Illustrate the memory address range where the chip with 256 bytes in the memory where explain how the range can be changed and modified. Hardware of the chip selection, which is known as the CS function, is always the active low for the line. That means when the voltage is low, then it will become active. The memory chip has 256 registers. Here 8 address lines are from A7 to A0 and one chip selection which is known as the CS, which is active low, and then the two control signals, which is the write and read function. Read is also active low, write is also active low. Here the address line is from A7 to A0 and the remaining address lines are from A15 to A8. Here we use one chip selection and those lines are called as a high order address lines. Those lines are called as high order address lines. By this diagram we can see that here we have address lines from A0 to A15. In this section we have all are zeros. So the starting position is 0000 and the destination is 00FF, where the first 4 bits and another 4 bits denotes 0 and then again 0 and then 1111. Those 4 bits are known for F and those 4 ones are also known for again F. In this section we can easily see that those 8 bits are for the register selection and first 8 bit are for the chip enable or chip selection. By this diagram we can see that here we have the memory read section, which is active low, memory write section, which is also active low, and here the chip selection comes from the high level where we use the address line which is A8 to A15. From A8 to A15 is work for the chip selection or CS section, and then A0 to A7 are for internal decoders which are directly connected with 256 register sections, and then lastly we have the IO section. This one is the memory address range where we have 000 to 00FF. By this diagram we can easily understand how we done it. This one is the 0000 and this is for the 00FFH. Here we have put it all values 0, but using this NOR gate this will generate all values to the 1, and finally we get the FFFF. Now we are in the example number 2. Here we can see that here we have the memory address range is of 1 kilobyte. That means 124 into 8. Explain how the range can be changed or modified and chip selection in line can be modified. By here we can easily say that we have the memory chip register which is 1024. That means it has 8 address line which is from 0 to A9 for generating 1024, because 124 can be generated by 2 to the power 10. That means A will occur from 0 to A9, that is the 10. because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is known as equals to the 10. So 2 to the power 10 can be generated by A9 to A0. That is why we have only one chip selection and two control signal as read and write section, and the remaining address lines are from A10 to A15. Here we have the starting position is 0000. That's why we have 16 consecutive zeros, and this the highest range can be 11111. That means we have from A9 to A0 all are ones. We generated the 3 if, because this 4 is for an if, which is the first one, then again 4, then again 4 1 generated another f, and then 1 1 generated the 3, and then lastly the continuous 6 zeros generated a 0. So the highest value can be 03FF. In this diagram we can easily say that this one is for read section, write section, IO section, and in the internal decoding section we have A0 to A9, and in chip selection section we have from A10 to A15, where all zeros are inputting, and by NOT gate they are transmitted to 1, and then the control signal is generated. Now we are in the memory and interfacing fetch section. By this fetching section we have an example that the instruction code is 01001111, which is 4FH, is stored in the memory location 2005 and instruct the data flow of list sequence even when the instruction code is fetched by the MPU. By this section we need to follow some instruction first, then we can describe this diagram. The program counter places the 16-bit address, which is 2050 hexadecimal of memory location, on the address bus. So first we will generate the address on the address bus, which is 2050. Then the control unit sends a memory read or MEMR, which can enable the output of the buffer. Then the instruction 4H is stored into the memory location on the data bus and transfer section for decoding microprocessor, and then lastly the instruction is decoded and executed according to the pattern. So first of all we need to generate the address on the address bus. Here we have the memory section, which is from the 2000 to 2005, and here is the programming section. By this programming section we generate an address by the address bus and we send the address to the memory location. Then by the control unit it generates a control signal which is sent to the memory section. By this control signal which we have sent the memory read section, then the memory read section and address bus will combine and then put the data, which is 4F, on the data bus. The data 4F will transform by the data bus to the internal bus, and by this internal bus section it will move to the decoding section, which is the instruction decodation or decoder. By this decoding section it will move to the execution section and the program will be executed. That is how this works. This diagram is also very important for your examination. Please have a snap of this one. Now we have the memory classifications. First of all we have primary memory and then we have the secondary memory. Primary memory are those memories which are used for executing and storing the programs, which are the read-write memory, that means the RAM, and the read-only memory, which are the ROM. We have two types of RAM: static memory and dynamic memory. Static memory doesn't need refreshment but dynamic memory needs the refreshment. Here we have some descriptions of static memory. It is used by the flip-flop and it is dependent on the voltage and the lower density but the higher speed. And here we have 6 transistors. It is also known as the cache memory, but in dynamic memory we have high density, low power. It is the cheaper than the static memory, which it is also known as the synchronous dynamic RAM, the rambus RAM, etc. Those are the examples of dynamic RAM. And in this dynamic RAM we also use some capacitors instead of flip-flops. Here is the diagram of memory section. First of all, memory, then primary and secondary. In the secondary sections we have dividation, and in primary section we also have dividations. You can easily see the diagram by this. Have a snap of this one. Now we are in the ROM section. In the ROM is for read-only memory. Here we have the masked ROM, which is cannot be removed or programmed, and secondly we have the prom, which is programmable ROM. And ROM is also non-volatile. That means if you turn off the power of your computer, the values are stored in ROM will not disappear. prom is programmable ROM. That means the ROM is programmable, that can be changeable. But in eprom we have the electric programmable ROM. That means that this ROM can be programmed by electrical section. eeprom, that means electrical erasable ROM. That means that electrical erasable ROM can generate it or created programs or remove it by some electrical components, and it can easily be erasable, but others are not erasable. There are some lines on prom, eprom and eeprom. Here are some description on flash memory. Flash memory is in the erasable procedure. Flash memories are known as the CD or the memory pen drive. Those are known as the flash memories. Now by the storage capacity we have secondary storage and backup storage. Secondary storage is the main hard disk and the backup storage is known as the cloud sections. This tri-state inverter are known as the flip-flop because they generate the same value again and again, and that is why they are known as the tri-state inverter, because if you put 0 here you will get output 1 here, and if you put 1 here in the input section you will get the output 0. That is why this is known as a tri-state inverter. Now the buffer section. Buffer is the logical circuit to amplify the current or the power. It has one input line and one output line. By this diagram you can easily understand about buffers. Now the decoder section. By this decoder section we can generate the main value which was encoded previously. Suppose your friend is sending an data to you and he encoded it, but in decoding section it takes the input from 2 lines and generated a 4-bit output. That means it is known as 2 to 4 decoder. The output number depends on the decoder section. Here it is from 2 to 4 because it have 2 input and 4 output. Now the encoder section. Here the input is much and the output is low. Here we have 8 inputs and 3 outputs. That is why it is known as 8 to 3 encoder. Now the D flip-flop section. It can be latched or clock. If it is connected with a clock like this one, then it is known as the clock section, and If it is not connected with the clock, then it is known as the latch section. By this diagram you can easily see that here we have one input and here also we have one input, but in this section we have a direct clock connection, and in this section we have the previous one, then the clear section, and then also the inverse of the clock. So that's the two type of D flip-flops. Here is the diagram of flip-flop. That's for today. Thank you.